Welcome to Lesson 11D, Grade Efficiency. This will be a short lesson. We need to just define grade efficiency, which is something that we're going to use a lot through the rest of the semester. I'll also define something called cut diameter. When we're talking about settling of particles in a container or a room, we had this critical time, and then we had two different equations, one for laminar and one for well-mixed settling. So we had an equation for the removal efficiency, eta, in both cases. These are all for one particle diameter, dp. Now imagine repeating for some range of particle diameters. In other words, for a polydispersed aerosol. Consider some time t1, and let's just look at settling in a little container or a room. All the particles are initially distributed randomly and uniformly, but at time t equal t1, some of the particles have settled. So if this is a small dp, we have some small value of vt, and maybe only 20% of them have been collected at the bottom or removed. Now consider some medium particle diameter. More of the particles will have been removed because the VT is greater. So there will be more of these on the bottom, more will be removed, so the eta will be larger. We can think of an eta at some dp1, an eta at some dp2, and now a third case with some large dp. Here nearly all the particles have settled, and the VT is much larger. We can call that eta dp3. So eta is in fact a function of dp, and that's all that grade efficiency is. So grade efficiency is just eta as a function of dp. This will apply to filters and other kind of particle removers and any other kind of device that tries to remove particles from a flow or from a room or whatever.
But sir, what does that have to do with our grades?
No, not that kind of grade, Ned. This is grade like when you grade eggs, from small, medium, large, extra large.
Oh, thank you, sir.
You're welcome, Mr. Nerdly. So let's take these same equations that I have up here, and instead of eta, we put eta dp. That's the grade efficiency. Now let's plot the grade efficiency at our time t1, which I had illustrated up here. So we plot eta dp as a function of dp. We'll typically use percentage, although remember that in these kind of equations, eta is not a percentage. It's a number like 0.2, which you would convert to 20%. Let's put a couple values on here, 100%, 50%, and 0. So what do we expect this grade efficiency to look like? Well, for the laminar case, we expect it to look something like that. It goes up until it reaches 100%. It can't be greater than 100%, so it's flat from there on. This is laminar settling, which, by the way, is what I was illustrating up here, the laminar settling case. At some time t1, we will have a removal efficiency for every different particle diameter. We can define this as some kind of a critical diameter because for dp bigger than this critical diameter, we have 100% removal. So eta dp is 100% from there on. Looking at our three cases up here, dp1, dp2, and dp3, these look like about 20%, 50%, and maybe 80%. So these would be somewhere like this, dp1, dp2, and dp3. What about the well-mixed case? Well, it'll look more like this. This is typical of the type of curve you get for the well-mixed grade efficiency. Some people call it an S-curve because of its shape. Looks sort of like a flattened out S. Now I want to define one more thing, and that is the cut diameter. dp cut is defined as the diameter dp at which the grade efficiency is exactly half, or 50%. So this is our 50% line. So you see we have a cut diameter for the laminar case, and that is approximately dp2, dp cut for the laminar case. And we have a different dp cut for the well-mixed case. In fact, it's larger. Depending on whether it's laminar or turbulent, we can define a cut diameter where the efficiency is 50%. So we're going to use this terminology from now on. We're going to always be plotting eta dp. So I wanted to introduce it in this short lesson. And now I'll do a quick example problem. We have some container of height h, initially well-mixed polydispersed aerosol of spherical particles. The air is quiescent, and then we have temperature, pressure, the height of the container, and the particle density. We want to calculate the particle diameter in microns at which 40% of the particles are removed after 30 seconds has elapsed. So first, I wrote out the equation for laminar settling because this air is quiescent, there's no mixing going on. So the appropriate grade efficiency is this laminar one. Here's the critical time, and then here's the grade efficiency. The Problem is we don't know dp. And I'll just sketch what's going on here. We have some kind of a container with height h, and just like I sketched in those 3 cases, at some particular dp, eta dp is 40%, which is what we're after. But we don't know dp. This is at some time t1, which we're calling 30 seconds here. This is going to involve some kind of iteration. I'm going to show you the procedure to do this, but not show you exactly how to do it. I want you to do this on your own and make sure you can come up with my same answer. The first thing, step 1, is to calculate the air properties. You know how to do that. At this temperature and pressure, we get rho, we get mu, we get lambda. You know how to do that. Now let's guess some value of dp. For this dp of our guess, we have to calculate settling speed, vt, which fortunately you have programmed into your software already. So we use our standard iteration procedure involving Knudsen number, Cunningham, Reynolds number, CD, and vt, and calculate vt at this value of dp. Calculate the critical time and eta of dp, which is just t over tc, where this t is what I call t1, which is our 30 seconds from the given information up here. Now, unless you're really lucky, this will not be 40%. The next step is to compare eta dp with our desired eta dp, and they won't be the same from your first guess. So now you have to iterate and solve for the correct dp that yields eta dp equal 40%. How? I'll say any way you want. Trial and error. Just pick some new dp, do everything again. If you're using software, this is pretty trivial. Come up with another dp. It's not right, but maybe you're closer, and you keep trial and error until you get it right. That's one possibility. You can use the false position method, which I showed you before, which is kind of a glorified trial and error procedure where you do your next trial logically and systematically rather than just pulling something out of the air. Use Excel's what-if analysis. If you're using Excel, you can plot the grade efficiency as a function of dp. Just make a table and plot eta, and then just pick off of your plot where eta dp is 40%. You can make some iteration scheme like we did for calculating VT, where you start with a guess and then somehow you come up with an equation for a new DP after step 5, and then go back to step 2 and repeat for a new DP, and then hopefully that will converge fairly quickly also, or any other way you can. Some software packages will iterate for you to find the answer. However you do it, you should get 41.3 microns as your DP. And make sure you can do this before you try the quiz or homework, etc., as usual. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.